A garden hose-sized cable can carry a continent's conversation, and one fails somewhere in the world roughly every other day. Yet the internet usually keeps moving, because failure is not a surprise. It is part of the design. Now comes the real trick. A cable cannot dodge its own broken section, but the surrounding network can. Operators provision protection paths and alternate capacity. When a link is lost, traffic can be shifted onto another cable or a terrestrial path. That is why a repair lasting weeks need not mean weeks offline. But rerouting is not magic. If the alternatives are missing or already full, users may see congestion, a longer path, or a complete outage. Follow one packet through a failure. Before the cut, a router sends it toward the shortest available transatlantic path. The fiber goes dark. Monitoring at the terminal raises an alarm, and protection equipment or network control removes that path from service. The next packet is forwarded toward a different landing station, perhaps over terrestrial fiber before it reaches another ocean cable. Nothing inside the packet changes, only the sequence of links carrying it does. If the alternate path has headroom, the detour may add only distance and latency. If it is crowded, queues grow, video quality drops, and some sessions time out. This is why a cable map alone cannot tell you whether a cut becomes invisible or disruptive. The decisive questions are how many paths are genuinely independent, how quickly traffic shifts, and how much spare capacity exists when everyone needs the backup at once. To see what the network is protecting, start with the scale. The ITU says submarine telecom cables carry more than 99% of international data traffic. Satellites matter for remote coverage, broadcasting, and backup, but the everyday flow between continents mostly travels through glass on the seabed. Depending on its destination, a message leaving your phone can cross local and terrestrial networks, reach a coastal landing station, and enter one of these ocean routes. At the center are hair-thin silica fibers. Around them sit layers chosen for the route: strength material, water barriers, a copper conductor, polyethylene jackets, and, where danger is higher, steel armor. In stable deep water, the cable can be surprisingly slim. Near coasts where anchors and fishing gear work, it gains armor and may be buried. There is no universal cross-section. Engineers match the build to the seabed and the hazards. The data travels as laser light, guided through the glass by internal reflection. Multiple wavelengths, think distinct colors, though not necessarily visible, can share one fiber through wavelength division multiplexing. That increases capacity without requiring a separate strand for every stream. But light weakens across an ocean, so sealed optical amplifiers, commonly called repeaters, boost it along the route. Electric current sent through the cable's conductor powers them from the terminal stations. Long before that light turns on, survey teams study depth, slope, sediment, currents, seismic activity, fishing grounds, existing cables, and landing access. The route is chosen to avoid hazards where possible. In suitable shallow water, a plow or remotely operated vehicle can bury the line. Far offshore, a lighter cable may simply rest on the seabed. Protection begins with geography, not just metal. At shore, the cable does not plug straight into the public internet. Inside a landing station, terminal equipment sends and receives the optical signals. Power feed equipment energizes the repeaters, and network gear connects the submarine system to terrestrial links or other cable systems. The wet plant under the sea is only one part of the chain. The landing station is where ocean infrastructure becomes an ordinary network connection. Redundancy is not simply a cable count. Two lines that share a narrow corridor, the same beach, or one landing station may share a failure. That is why the 2026 Porto Declaration calls for varied routes and redundant landing points, not merely more capacity on paper. The ITU warns that places dependent on a single landing point face greater interruption risk. True diversity means the backup does not inherit the same weak point. That resolves the apparent paradox. An individual cable is a long, slender object exposed to ships, geology, and the weather. The internet is a network of paths, operators, landing sites, and repair agreements. The first can be physically fragile, while the second remains dependable. Armor lowers the chance of a cut. Diverse routes lower the consequence. The resilience lives in the architecture and the response. Cable faults are routine, not rare. In 2026, the ITU and ICPC put the global rate at around 200 a year, with more than 80% caused by fishing and anchoring. Natural hazards such as earthquakes, storms, and seafloor currents, plus equipment failure, make up much of the remainder. Deliberate damage is possible, but the everyday baseline is mostly accidental. That matters because protection has to work during ordinary maritime activity every week. Charts, route planning, armor, and burial reduce the odds. None makes a cable invulnerable. When a fault occurs, monitoring from the terminal stations helps narrow its location. Engineers use optical and electrical measurements to identify the damaged section. Then a digital problem becomes a maritime one. A repair ship, spare cable, trained crew, permits, a workable sea state, and time to reach the site. On site, the ship holds position without dropping an anchor onto the very infrastructure it came to fix. A grapnel or remotely operated vehicle helps locate, cut, or recover the cable. The crew brings the ends aboard, removes the damaged portion, splices in a tested replacement, and returns the repaired section to the seabed. In deep water, this is precision work performed from a moving surface, often with kilometers of cable below. ITU design guidance estimates a mean repair time of 1 to 3 weeks, but that is a planning range, not a promise. Location, water depth, vessel availability, the cause of damage, and weather can all change it. Regulatory approvals can delay when a ship even begins. This is why spare parts, maintenance agreements, trained crews, vessel access, and predictable permits belong in the same resilience plan as the cable itself. While that work happens, the network faces its real test. If independent routes have enough headroom, traffic stays on protection paths, and many users notice little. If a region relies on one landing point, or if several supposedly separate links share a choke point, the same cut can be far more disruptive. A system can survive and still slow down. Resilience is not a binary label. It is the amount of failure the design can absorb. So what keeps the internet running? Not one indestructible tube. It is a stack, glass carrying many wavelengths, amplifiers powered from shore, armor and burial where risk is highest, landing stations joining sea to land, networks prepared to reroute, and crews prepared to repair. The system works because engineers assume components will fail and build several ways for communication to continue when they do. The next time a call crosses an ocean, remember the quiet relay beneath it. For a follow-up tracing one packet from phone to seafloor and back, subscribe and tell us which ocean route to follow.